Hi students, welcome to the next topic from magnetic effect of current. So far we have learned about Biot-Savart's law and its application, how we can make use of the Biot-Savart's law to find various magnetic field due to a current carrying conductor, like finite current carrying conductor, infinite current carrying conductor. Now today we are going to see the next topics. We are going little ahead, like the second part of magnetic effect of current, the second law, and that is called Ampere's law. So Ampere's law in magnetism is a kind of successor of Biot-Savart's law. Why it is called a successor means Biot-Savart's law has its own advantages and the equation is little bit complex comparable to that of that of Ampere's law. So we will see the things in which we have seen with respect to Biot-Savart's law, we can also see with respect to Ampere's law. So there are actually three things we are going to see, and we are going to solve one tricky question which are asked for the JEE main examinations. Okay, so this is what the first part or the first intro part of Biot-Savart's law is expected to be continued. Okay, so let's start. You can write out the heading Ampere's law. Ampere's law. Okay, what is this Ampere's law? Of course we know Biot-Savart's law on another side. So we have Biot-Savart's law. Biot-Savart's law we have. Here we have written the equations. dB is equal to mu 0 by 4 pi I dl sine theta divided by r square. This already we have seen before. Okay, so magnetic field due to current carrying conductor, whether it's a finite length, whether it's an infinite length, whatever it is, it's possible to solve it. But here this law is, with the help of this law also, it is easy to find it out, the magnetic field due to a current carrying conductor, infinite conductor, solid conductor, hollow conductor. There are a lot of stuffs. But what is this law specifically states? So this law states that closed integral of, this indicate, as like I told in Gauss's law, we need to have a closed path. In electrostatics I told we need a Gaussian surface. Here this closed path, here it is called an Amperian loop. So integral B dot dl is equal to mu 0 times of current enclosed IENC. I written as IENC, current enclosed. I will tell you an example. Let's assume we have a current carrying conductor, and the conductor here the currents will be there. Okay, suppose you can assume a current carrying conductor is placed like this, as like this pen. Okay, so what will happen? Current carrying conductor is placed as like this pen and the currents are going inside. So how will you find out the magnetic field? Using the right hand thumb rule. So thumb is pointing into the board, in the direction of board. You can look here, thumb is pointing into this one. So my all other four curling fingers are rotating like this. So thumb is inside, curling fingers are rotating like this. So with respect to this point, magnetic field is like this, right? Magnetic field is like this. Let's assume another situations. So magnetic field like this. So at this point, the same directions, at the bottom point, the magnetic fields are like this. So here the magnetic fields are like this, B. This is the direction of magnetic field. This is the direction of magnetic field. So your fingers and the top side, it is like this. Here it's curling like this. So the magnetic field like this. So it is like a tangent. Magnetic field is tangential if the currents are going into the board. The same case will be there. Suppose into the board, current direction is taken as positive. For example, I am assuming it is positive. Let me assume the another situation, the currents are going out. And this I will say currents are going out means currents are in the negative directions. The currents are going out. If you are keeping like this one, everywhere your magnetic fields are reverse directions. So with respect to this negative one, with respect to this negative one, the magnetic fields here opposite, here opposite, here opposite, here opposite, everywhere it is opposite with respect to negative. So current direction changes, which means internally the magnetic field directions are changes. Now let's come to the formula. Current direction is same as the direction of the dl vector. Okay, so here I have one direction of magnetic field. Direction of magnetic field for the black line, it is in clockwise direction like this. And the currents are into the board. So current have one direction and magnetic fields will have one directions. Okay, so B dot dl. So dl means, suppose I am assuming the current direction is also given the direction of dl. So that this is a dl. dl is in this direction. This is a piece. So dl is a small current element in this direction. So dl is a current element in this direction. dl is a current element in the black direction. So all are black. So B dot dl, B is in this direction, dl is also in this direction. Suppose this is the direction of the length vector given by this current. So what is a dot product will give? Dot product means A dot B, AB cos theta. B dot dl, B dl cos theta, both are same direction, theta equal to 0 degree. Now we'll take another case. Current direction is changed. Current direction is changed means dl direction is also changed. So in some other cases, current direction changes means dl direction also changes. So dl direction also changes. dl direction. So this is the B directions, and here the dl direction also changes. So here previously we have one dl in this direction. So now the dl direction also changes. Now if you see the black lines, B in the direction, dl in the same direction, B dl cos theta, theta equal to 0 degree. If you see the red color line, magnetic field reversed because current is reversed. If current is reversed means dl will also reverse. So dl is reversed, magnetic field is also reversed. So the angle between B and dl is again equal to how much? 0 degree. That is again equal to 0 degree. If both are equal to 0 degree, then in both cases, if currents are going into the board or currents are going out of the board, in both cases the dl directions are changing because of the change in the direction of current. Because of the change in the direction of current, the direction of dl is also changing and the direction of magnetic field also changing. So always the angle between B and dl is equal to how much degree? 0 degree in this case. So B dl equal to mu 0 by mu 0 I enclosed. So in this example, when theta equal to 0 degree, what is this indicate? B comma B and dl in same direction. In same direction. B and dl are in same direction. So what we can write? Closed integral B dl cos of 0 equal to mu 0 times of current enclosed. Closed integral B dl equal to mu 0 times of current enclosed. This is the formula. So we have another side will be there, right? So angle between, in another way, angle between B and dl is equal to 90 degree, or I can say it is equal to pi by 2, both case 90 degree. Then what is cos 90? Closed integral B dl of cos 90 is equal to mu 0 times of current enclosed. So this is equal to what? B dl cos 90. What is the value of this one? This is equal to 0. So 0, in short, it is indicate there is no magnetic field. 0 equal to mu 0 times of current enclosed. If the angle between B and dl is perpendicular to each other, then there is no current, there is no magnetic field exist, which is equal to 0 degree. So this is the meaning of this one. In order to apply this law, you need an Amperian loop. So this represents an Amperian loop, something like a Gaussian surface. This is what we are learned from here. Now what we are going to do means we have to understand one more term, current enclosed. Current enclosed means you are considering this as an Amperian loop. So in the Amperian loop, current must be there. So you can see this is an Amperian loop. So within the Amperian loop, a current is there. Yes, current is there. Current is going into the board. Current is going out of the board. The red one is dot means out. Plus means into the board. The cross mark is into the board. Dot means out of the board. So the condition, the primary condition is that within the Amperian loop, within this loop, it must be, or it is required to have. It is required to have a current within the loop. That's what it is written as ENC, enclosed. Enclosed where? Enclosed within the Amperian loop. Within the Amperian loop, you are looking at no current. No current means magnetic field equal to 0. So magnetic field can be 0 in two conditions. First condition, the angle between B and DL should be equal to 90 degree. Then complete factor will goes to 0. Condition number 1. Condition number 2, within the Amperian loop, if there is no current, current enclosed, this is a concept, current enclosed. If no current within the Amperian loop, then this is equal to 0. So I can say B equal to 0 in two conditions, condition number 1 and condition number 2. Okay, the first one, within Amperian loop, you can write within Amperian loop. Within Amperian loop, no current. Within Amperian loop, if there is no current, magnetic field is equal to 0. Second condition is what? Angle between B and DL. Angle between B and DL is equal to 90 degree. In both these condition, the magnetic field will goes to 0. Hope this concept is clear to you. So let's move to the next topic. I mean the application of this Ampere's law. Okay. So we'll say first I have to clear the board. So hope you understood what is Ampere's law. Closed integral B dot dl will be equal to mu 0 times of current enclosed. Okay, that closed path is called what? Amperian loop. Okay, same thing we have learned in electrostatics. There it is called what? Gaussian surface. Exactly the same way. There is no difference. The name only different. Both cases it should be a closed path. Okay, that's all. So we'll move to the next topic, and that is called the application of Ampere's law. Application of Ampere's law. So you can write out the heading, application of Ampere's law. Application of Ampere's law. Okay, so there are some subheadings will come. This is the main heading, application of Ampere's law. We'll move to the first subheading. So the first subheading over here, application of Ampere's law means with the help of Ampere's law, what are all the things I can generate, or how Ampere's law help me to find out different scenarios magnetic field intensity. So let's take one example. So let's start with the first one. Magnetic field, you can write on the heading, magnetic field at various point, magnetic field at various point in a solid cylinder, in a solid cylinder, magnetic field at various point in a solid cylinder. What this is mean to us? So let me consider an infinite cylinder, and this is going like this, not ending at all. This is going, and this is solid. Okay, so solid means it is filled with an iron material or whatever, a copper metal, whatever it is. It's a filled solid. One example of a solid cylinder is, best example of a solid cylinder, our normal copper wire, which we are used to pass the electricity for our fans, light, air conditioner, refrigerator, TV, etc. So we are going to find out magnetic field at various point in a solid cylinder. Various point. 3 points I am considering. Okay, one is inside, one is surface, and one is outside. So this is an inside point. So we have a central axis. I have a central point. So I am assuming this is a central axis. Central axis is passing. So central axis la at a distance of, so I need to find out magnetic field here. To find out magnetic field will be here, I need to have what? You can use Biot-Savart's law, you can use Ampere's law, but Ampere's law is quite simple. Why means, if a point is given, immediately you have to consider that point include an Amperian loop. So this red one is an Amperian loop. If you want to find out magnetic field will be here, you will consider this as your Amperian loop. If you want to find out magnetic field will be here, you will consider this as your Amperian loop. Okay, so there is 2 points will be there. Suppose the inner point, the inner radius is taken as r dash, outer radius is taken as capital R, and this outer distance is called r. So r dash is the inner point, capital R is the original radius, and r is the outer radius. Now we are going to find out magnetic field at various points. So magnetic field, so B inside, magnetic field inside we are going to find out, magnetic field inside. Okay. So first we will write the law, closed integral B dl cos theta equal to mu 0 times of current enclosed. You have to assume for the complete cylinder, I amount of current is passing. Complete cylinder, I amount of current means you can assume there are, just an assumption only, you can assume there are 100 electrons are there within the complete pipe. Okay, now our circle is over R. Our circle is over R dash area only our Amperian loop. So if you have 100 electrons are contributing to this current I, then how many number of electrons are passing through this small Amperian loop? All the 100 electrons will pass? No, because some electrons are passing here, some electrons are passing here, and out of 100 some number will pass, will be here. It may be 10, 20, 30, 40, etc. But it's not 100, that is sure, pakka sure. If it is 100, if it is 100, then I can write I will be there. But what is a current enclosed? Here we have to use some concept. For example, what is the total surface area of this one? Pi r square is the area. Pi r square meter square. The unit of area is meter square. So pi r square meter square area will have how much current? I amount of current. So pi r square means 1 into pi r square. Correct. So 1 meter square will have how much current? I divided by pi r square amount of current will be there. 1 meter square. What is our area? Our area is this 1 into pi r dash square. So pi r dash square is our surface area. It's a circle, right? Surface area. So with this area, how much is the current coming? I divided by pi r square. Here I multiplied with the pi r dash square. So left hand side multiplied means right hand side also I have to multiply pi r dash square. So this pi get cancels. So what is the amount of current? I r dash square by r square. This is the amount of current is available within the r dash circle, not the full current. If I am asking what is the current in this area, you will say hi. What is the current in this area? It is not I. It is a part of I. What is that part of I? This is a part of I. Pi r square area will containing I amount of current. So 1 meter square means small 1 meter square area, this much area. This is called 1 meter square area, this small one. How much current will be here? 1 meter square means this pi r square will go to right hand side, become division. Now what is our area? Our area is pi r dash square area. So pi r dash square multiply with the left side and right side. So I will get pi r dash square area is containing I into r dash square divided by capital R square amount of current. This is the current available here. Now we'll continue. So closed integral B dl. Of course I know the current is passing in this direction. So I am holding my fingers. So it is just okay, this is a current and current is passing upward. So I am holding my fingers. So my fingers are just touching over the surface, tangential. Length is also tangential like this, as I told before. So what is the angle between B and DL? What is the angle between B and DL? See, B is like this and DL is a small piece which is also like this. So angle between BDL is 0. So BDL cos of 0 will be equal to mu 0 times of what is the current will be there? I into R dash square divided by capital R square. I into R dash square by capital R square. So B dl for a circle, what is integral dl for a circle? dl is equal to mu 0 I into r dash square by capital R square. dl for a circle is, what is the circle will be here? This is a circle. For a circle, what is length? 2 pi r dash is equal to mu 0 I into r dash square by r square. R dash and r dash will get cancelled. So B is equal to mu 0 I r dash whole divided by 2 pi r square. This is the equation for magnetic field intensity inside the solid cylinder. Solid cylinder best example on copper wire. Normal our copper wire which we are used to pass electricity, connected to our fan, light, to everything. All the home appliances are connected with copper wires to pass electricity. So this was a case will be here. Okay, hope this is clear. Magnetic field inside the conductor, what is difference will be here? Current is playing the role will be here. Because why? Because current is not the full current, it is part of the current will be here. So this is clear. Mu 0 I into r dash divided by 2 pi r square. This is not over. I need to do some little more derivations to make it a perfect solution for this one. This is one of the equations. You can further simplify if you would like to have. How you can simplify? See, we know current density is equal to current by area. Ij equal to current density. This is called current density. I would like to ask one questions will be here. Have you heard about the term called capital J in first year? There is one term in first year which is called capital J, and there it is called impulse. There it is called impulse. First year you will learn one term called impulse. Force into time is called impulse. Very important for Neet and JE. So here it is called current density. So let's go. So I by area, which means I by pi r square. So this I by pi r square I can replace with current density. So my formula is equal to mu 0 J into r dash divided by 2. Mu into J. J means I by pi r square. This I by pi r square is replaced with this one. So this is an alternate expressions to find out magnetic field intensity inside the solid cylinder. Both are exactly same. No difference will be there. Only difference is like that. I by pi r square we are replaced with the current density equations. Okay. So now it is clear. So but here one important point, one highlighted point, magnetic field intensity is directly proportional to r dash, which means r dash is increasing, magnetic field is increasing. See, at the center, if this black dot is my point, this is my point, right? This is my point. If the black dot is at the center means r dash is equal to 0. R dash is equal to 0 means magnetic field is equal to 0. But if you are going away, this point magnetic field higher, this point magnetic field higher. If you reach on the surface, magnetic field is very higher, maximum radius your magnetic field will be very higher. So I have to continue from here. So I will keep these equations. I need to do the rest of the derivations. So magnetic field, I understood what is a magnetic, what is a current density based formula for magnetic field intensity. Next I am going to find out the magnetic field intensity at the surface of the conductor. Magnetic field at the surface. At the surface means if the point is reached at the surface, r dash equal to capital R. So if I substituted in the same equation here, mu 0 I into r divided by 2 pi r square, r and r will get cancelled. B equal to mu 0 I divided by 2 pi r. This is also important. Magnetic field at the surface. Okay, so let's continue. So I got surface, I got inside. Okay, now I am going to find out magnetic field where? Outside. So magnetic field is going to find out outside. What's the formula again? B dl cos theta. Cos theta is 0. So closed integral B dl cos 0 will be equal to mu 0 times of current enclosed. See, you look, you are now in this. Outside means you are here. So within this circle, what is the total current? It's called I. So you can directly put it as I itself, mu 0 I. So now B into closed integral dl is equal to mu 0 times of I. What is closed integral dl for this bigger circle? For the bigger circle, closed integral dl for a circle is what? Suppose, see, you have a wire. Okay, you have a wire is equal to, length is equal to 1 meter. Then I can say, if you connect this wire like this, two wire you connected, then I can say the perimeter of the circle 2 pi r is equal to 1 meter. That is a basic principle. Both are same, right? This is called the perimeter. You have one wire 1 meter. That circle like connected to a circle. So if you connected to a circle, it's again 2 pi r. So the same thing you doing, length integrated, small length integrated means big length. DL integration become L. L is equal to what? 2 pi r. So this is nothing but L. L equal to 2 pi r. That's what we are writing as 2 pi. What is coming as R dash, capital R or R? This R will come because now we are at outside. So mu 0 I. So B is equal to mu 0 I divided by 2 pi times of small letter r. This is a magnetic field intensity outside. Okay. Now what we are going to do? We are going to draw some graph. So magnetic field inside, I am writing it again, will be here for our EC axis. So B is equal to mu 0 I r dash divided by 2 pi times of r square. Okay. Now what we are going to see means, we are going to see the graphical representation. Graphical representations. We are going to see the graphical representation. What's the graphical representation? Graphical representation, inside is surface, outside. So we'll draw the graph. Okay. So x-axis and y-axis. So x-axis and y-axis. So 0, this is an inside point. Okay. So 3 point. Exactly, this is a surface point. And after surface, this is called outside point. So you know, inside at the center r dash is equal to 0. So magnetic field is equal to 0. So at the center, magnetic field is equal to 0. From the center, now if you are moving away from the center like this black dot, you are going away, r dash increases, magnetic field increases. So magnetic fields are increasing linearly. I will take another color. So magnetic, this is a magnetic field increases. Where is the maximum value will come? When r dash will be equal to r at the surface, mu 0 I by 2 pi r. So at the surface, this will have a maximum value. After the surface, if you are going away further, means your distance will be converted into what called r. Your distance is converted into r means B is proportional to, here you can see B is proportional to 1 by r. Here you can see B is proportional to r dash directly. That's what it is increasing. Now here outside it is inverse proportion. Inverse proportion means when r increases, B reduces. Inverse proportional graph, not a straight line. This is small inclinations like this one. So magnetic field at the inside it is increasing till the surface. After the surface it is reducing. The graph is a slight parabolic in nature, not a cut straight line. Okay. So remember like this one, x and y axis, and the y axis representing magnetic field, x axis representing the distance small letter r. So this is a graphical representation of magnetic field at various points in a solid cylinder. Example, a copper wire. It's a solid thick wire. Okay. Hope this concept is clear to you. So let's move to the next heading, magnetic field due to a hollow cylinder. So what we have seen about magnetic field due to a solid cylinder at various points, which means inside, surface and outside. Now we are going to see magnetic field due to a hollow cylinder at various points, which means for a hollow cylinder, it's inside, it's surface, it's outside. Okay, so let's have the diagram first. So we have an hollow cylinder and which is of infinite size, doesn't matter, and this is a central axis will be here, and this is hollow means inside it is purely empty, nothing will be there. So inside it is an empty space. So current will be passes where this is flowing a current of I amount of current is passing through this one. You can consider as like our normal PVC pipe, normal pipe, inside it is hollow, right? Surface only it is covered. So current is passing only through the surface. So we are going to find out magnetic field at various points. First one, magnetic field inside. Magnetic field inside means we have to consider like 3 points. One is an inside point, we are concerned an Amperian loop, we are concerned a surface point, we are concerned Amperian loop, we are concerned outside point, and we are concerned another Amperian loop. So this is a magnetic field and inside point. This is a surface point. This is an outside point. Okay, so 3 points. So magnetic field we are going to find out inside at a distance of r dash distance from the center, at a distance of capital R, at a distance of small letter r. So we are applying the Ampere's law, closed integral I know B dot dl is equal to mu 0 times of current enclosed. Now you have to see will be here. We know this B dot dl for a closed surface, normally we are taking the currents are going, so my magnetic fields are around the pipe, and the dl length is also around the pipe. You can consider this is current is going upside, I am holding my fingers, so the magnetic fields are just curling this pipe, and length is also taken in this way, not this length. So this is dl, all dl will give rise to what? L, integral dl equal to L is equal to what? 2 pi r. So that's what we are doing, it will be here. So this is closed integral B dl of cos of 0 will be equal to mu 0 times of current enclosed within the Gaussian, not the Gaussian, within the Amperian loop. Is within this loop any current will be there? No, because current is only flowing through the outside. So current equal to 0, hence magnetic field equal to 0. This is magnetic field at inside point. Now we'll go to the next one, which is magnetic field on the surface. Magnetic field on the surface of the conductor. So closed integral, I am again writing B dl cos 0. This should be careful always, it's not cos 0, depends upon the question. Mu 0 times of current enclosed. See, within this path any current, yes, within this path on the surface current is flowing. What is the current? I is the amount of current which is flowing through the surface. So mu 0 times of I. So we know B is equal to closed integral dl will be equal to mu 0 times of current. What is integral dl? Integral dl equal to 2 pi r. So B into 2 pi capital R will be equal to mu 0 times of chi, and B is equal to mu 0 I divided by 2 pi r. This is the magnetic field intensity due to the surface equation, B equal to mu 0 I by 2 pi r. Now we are going to find out magnetic field at outside. Magnetic field at outside, again we know closed integral B dl cos 0 will be equal to mu 0 times of current. Within this red color any current is passing, yes, current is there, I is the current, so I. So B into closed integral dl equal to mu 0 times of I. So class, what is closed integral dl? dl equal to L is equal to perimeter, which means 2 pi r, small letter r, because now the radius is small letter r, is equal to mu 0 times of I. So B equal to mu 0 I by 2 pi times of small letter r. Now we got the magnetic field intensity at various points inside the surface, outside. Now we are going to see what is a graphical representation of this one. Graphical model or graphical representation, you can write any heading. So what is the graphical representation is stating x-axis and y-axis. Y-axis magnetic field, x-axis is the distance. How many points we have? We have an inside point, and we have here surface, this point is exactly on the surface, and here we have an outside point. So inside point, let me make this to be clear. Okay, so here we have different points. One is inside, then we have surface, then the rest of the things will be here outside points. Inside, surface, outside. What is the magnetic field inside? It is 0. So magnetic field inside it is 0 means up to here it is 0, up to surface it is 0. On the surface we have a magnetic field, so it is rising to some value. And what is this value? Mu 0 I by 2 pi r is the value will be there. After the surface when r increases, which means you are going out of this hollow cylinder, you are going out of the hollow cylinder. When r increases, magnetic field reduces. As I told in the last topic also, it is not reducing in a straight way. This is reducing in a parabolic shape and tending to 0 Okay, this is the graphical model of a magnetic field due to a hollow cylinder at various points. The same case we have seen while we are studying for electric field intensity. Electric field intensity for a hollow conductor, the same graph. Electric field for a conductor, same graph. Electric field for a solid non-conducting sphere, the previous one what we have seen for a solid cylinder and their solid non-conducting sphere in electrostatics are same graph. While you are studying, you have to connect between these two. Hollow means inside no charge, no current. So graph between electrostatics and magnetism are same. Solid non-conducting sphere, which means inside it is filled. So graph is a straight line up to surface, then it is decreasing. Same cases for a solid cylinder in magnetism and solid non-conducting sphere in electrostatics. Graphs are same. Why? Because if charge will be there, only current will be there. So the graph between whatever you have studied in electrostatics, the same graph will becomes in magnetism also. Whether depends upon whether it is a hollow cylinder, whether it is a solid cylinder, the graph will be exactly leading the same fashion. Hope this is clear to you. Okay? Clear. Now we are going to see one question. Okay, hope this is clear. So mainly 3 sessions or 3 topics covered. What is Ampere's law, and magnetic field for a solid cylinder, magnetic field for a hollow cylinder at various points. Okay, hope you got the concepts now very clearly. Now we will do a question. You can write in a solid cylinder, the current density varies as J of R is equal to J naught times of R. What is the magnetic field intensity? Magnetic field intensity at a distance of r meter away. This is the question. In a solid cylinder, current density varies as J of R equal to J naught R. What is the magnetic field intensity at a distance of r meters away? So let's say we have a solid cylinder. Okay, so it's completely filled inside empty. So from the center at a distance of r meter away, we need to find out the magnetic field intensity. One point we have to add, R is less than capital R. Capital R is the radius of the cylinder. Which is the radius of the cylinder. So capital R is the radius of the cylinder. So small letter r is the radius. Okay. Now here I need to find out the magnetic field intensity. I assumed a Gaussian surface, but the condition is given. The current density varies which means that what? At when r equal to 0, at r equal to 0, which means at the center current density is 0. When r equal to 1 meter, let's explain. When r equal to 0, J of 0 equal to 0. When r equal to 1 meter, J of 1 meter equal to J naught. When r equal to, for example, 50, J of 50 equal to 50 times of J naught. Which means that what? J is the current density, current by area. So this current per area means if you are going from the center to away different meters, 0 meters, 1 meters, 50 meter, 100 meter, 200 meter, current density is keep on varying, keep on changing. So this is a mathematical equation. Correct. As I told you, some mathematical equations are coming in physics. Definitely mathematical equations are coming in physics. That should be what is called an integration or differentiations will be definitely involved in the solution. That is a hint for you. Normally these things we are very largely seeing in the chapter of laws of motion in first year. So J of r equal to J naught r. Now here what we have to do means, this is a common method, there is nothing different. I am assuming a small cylinder will be here. This small cylinder, black color I am expanding, will be here, and whose a small piece is cutting over here, which is at a distance of x meter away and having a thickness of dx. So now I can say current density or I can say di, small current will be equal to current density into small area, current density. So di will be equal to J into, what is dA? What is dA? dA is the area. For this one, how will you find the area? Perimeter into thickness. Perimeter is 2 pi x, thickness is dx. 2 pi x, see, if you see 2 pi r square is called area normally. So this first factor is called perimeter. So perimeter, and the second one is called thickness. So perimeter into thickness is called the area. Now how to get I from this one? Integral di is equal to integral j. Instead of j, this is at a distance of x meter away, at a distance of x meter away, not at a distance of r meter away. So why I am taking x means this x is varying from 0 to what level? 0 is a center. From 0 to what level x is changing? R. So that variation I need to know. To know that I have used these equations. You don't want to think about, hey sir, why you have written all of a sudden like this? No. The reason is like I need to find out magnetic field at this point, but I don't know what is happening in between from center to that point. I don't know. So I have assumed one arbitrary point. Arbitrary means any point x. So di equal to j into dx. Now we'll substitute j is equal to j naught r. Now it is not r, j naught x, because we are at x meter away. So 2 pi x into dx. Now we are integrating both sides. So what we will get once we integrate both sides? What we will get? Integral di will be equal to I. What is the limit from here? 0 to r. We need to go to 0 to r distance we have to go to. So I is equal to j naught constant, 2 pi constant, x square integral x cube by 3, integration limit is 0 to r. 0 to r. Now I will be equal to j naught 2 pi r cube divided by 3. This is the expression, upper limit minus lower limit. If you apply lower limit 0, then there is no second factor. This is the current. Now closed integral b dl cos of 0 will be equal to mu 0 times of current enclosed. What is the current will be here? This current I find out. The current within the distance of r, within r meter away. That's what first I hold on for some time, and I thought like then how, in order to find out magnetic field using Ampere's law, b dl I know it is equal to 2 pi r, because we need to find out at a distance of r meter. But how should I get the current? There is an hint is given to find out current, and that is this hint. At a distance of r meter away, you have this current density. At a distance of r meter away, At a distance of r meter away you have this current, but we don't need what is the current density at a distance of r meter. We need what is the current density within r meter away. That area we need. Here they are specifying at this point what is the current density at this point. This point means at a distance of r meter away. I need the current within this area, not this point. That is what I used integration, because a small point is given. From that one I need to get the whole current density within this area, which means I have to integrate. That's what I integrated. D I taken, a small area taken, then I do an integration. I got the full current within this area. Now I got the current. So B into integral closed integral dl will be equal to mu 0 times. So what is the current? Current is equal to J naught 2 pi r cube by 3. So B into 2 pi r equal to mu 0 J naught 2 pi r cube by 3. R and R will get cancelled. 2 pi cancel, R cancel, R cancel. So B is equal to mu 0 J naught R square by 3. This is the answer for this question. Mu 0 J naught R square divided by 3. This is the magnetic field intensity. The same model of questions will come for electrostatics also in case of a solid cylinder. This is a solid cylinder, and if you come up with some equations, always in general I am saying in physics, it will be end up with either a mathematical integrations or mathematical differentiations are involved in the sessions. Okay, hope this session is clear to you, and this is and understandable to you also. Okay, hope this is fine, and you got some insight into this one. J of r, which means the current density at this point is given. I don't need a current density at this point. I need what is the current within that circle. This point I don't need. I need within circle what is the current. That's what I taken a small area, I taken a small current, I integrated, I'll get a full current within the range from 0 to r. That current I find, and I substituted in Ampere's law. I'll get the magnetic field intensity within a distance of r meter away. Okay, so these are all the topics for today. Hope today's session is useful to you, and you got something new from me, and you learned something from me. And yeah, enjoy your study and have a nice day. Okay, bye, thanks.